back. We're going to do our second example on gravimetric stoichiometry. Hopefully you saw the first video about the formation of zinc sulfide from zinc and sulfur. In this example, it's going to look very similar. There's a slight difference, but overall we're going to use the same method to solve this problem. So once again, this is a very common practice in chemistry. We might have some target of product that we need to make. So in this case, we want to make 100 grams of iron metal, and we need to figure out what mass of ingredients we need to make that much iron metal. So first thing we need to do is, and I'll pause the video here, or you can pause the video as you're watching this, and think through what's the first thing you need to do. Well, the first thing you need to do is write a balanced chemical equation. And that starts off by writing out an actual equation with correct formulas. So first thing we start with is iron 3 oxide. It reacts with carbon monoxide, and it produces iron metal. So that's just iron by itself. And we make carbon dioxide. Now we would normally balance it, and that's what we're going to do, but this equation is a little bit trickier to balance than others. So I'm actually just going to go ahead and balance it for you. You won't actually learn how to balance. You could try balancing this on your own, and you'll get kind of stuck because there's a little bit more going on behind the scenes in this reaction, and balancing it requires a little bit more work. If you take Chemistry 30, or if you're an equivalent course, you'll learn about something called redox chemistry. Redox reactions, and this reaction is actually a type of redox reaction. This involves a transfer of electrons. So these reactions, to balance them, you need a little bit more work to do. There's a bit more going on underneath the hood. So I went ahead and balanced it for you. You do not need to know how to balance these types of these types of equations in Chemistry 20 or an equivalent grade 11 chemistry course, unless you're doing something called electrochemistry. So that being said, the equation is balanced. Let's figure out what we need to do. So we're being asked to solve for a mass of iron 3 oxide. So we need to figure out the mass of iron 3 oxide in grams. And we got to figure out how much is required to make 100 grams of iron metal. So how much is required to make 100 grams of iron metal? And you'll notice something important is in this write-up here. I'll draw your attention to it. We're saying assuming an excess of carbon monoxide. It's an important statement because it means that this means that we have more than enough carbon monoxide. So we don't really need to worry about how much carbon monoxide we have access to. The only thing we're really caring about is how much iron 3 oxide I need to run this reaction. We can kind of ignore carbon monoxide for now. So let's go and figure that out. How much iron 3 oxide we need. So we have a mass of iron, it's 100 grams. With everything, we need to convert it into moles. So to do that, we need its molar mass. And the molar mass of iron is 55.85 grams per mole. Moles of iron can be calculated using our mass of iron, which is 100 grams, divided by the molar mass of iron. And I'm using unit analysis here to make sure my units cancel out. So my final unit should be moles. So all my other units should cancel out. So you're going to get some answer here, 100 divided by 55.85. It's Let's just write out an approximate answer for what this is. Once again, you shouldn't be rounding your answers until you get to the last step, but we'll just kind of keep this number here as a reference for how many moles we have, okay, of iron. So we have 1.79 moles of iron. We have to figure out how many moles of iron 3 oxide were required to make 1.79 moles of iron. So this is where we get the mole ratio. So to convert between moles of iron and moles of iron 3 oxide, we need to apply the mole ratio. And the mole ratio is wrote it the wrong way, it's a 1:2 ratio. So that means there's 1 iron 3 oxide required for every 2 moles of iron. So 1 mole of iron 3 oxide is required to make 2 moles of iron. So in order to make 1.79 moles of iron, I should probably require a little bit less than 1 mole of iron 3 oxide. So I'll say that again. If 1 mole of iron 3 oxide is required to make 2 moles of iron, how much iron 3 oxide is required to make 1.79 moles of iron? Well, it's probably going to be a little bit less than 1 if you follow the ratio. All right, so let's figure out how much iron 3 oxide is required. And we take our moles of iron and we multiply it by the mole ratio. And this says we have 1 iron 3 oxide for every 2 moles of iron. So we're just multiplying it by 1/2, or you could divide by 2. So my number of moles of iron, I take that number I had. So it's, roughly 1.79 divided by 2. But I'm going to go back and recapture that number. So 0.895, roughly, round that up, it's roughly 0.90 moles. Once again, I'm rounding too much here. You shouldn't be rounding this much. You should only round to significant digits once you get to your final answer. Last thing we need to do is figure out the mass of iron 3 oxide, and I can do that by taking my number of moles of iron 3 oxide and multiplying by the molar mass of iron 3 oxide. So what is the molar mass of iron 3 oxide? Maybe I'll write it out down here. Well, I've got 2 irons, and they're both 55.85. And I have 3 oxygens, they're each 16. So let's figure what that is. 2 times 55.85 plus 3 times 16 is 48. So we get 159.7 grams per mole. So now let's go back and recapture that number. So first we figure out our moles of iron. So 100 over 55.85. There's our moles of iron. We divide this number by 2 to get our moles of iron 3 oxide. So this represents how many moles of iron 3 oxide we have or are required to produce this much iron. And now we need to multiply this number by the molar mass, because we have to figure out how much does this mole amount of iron weigh. So take this number and multiply it by our molar mass of iron, which is 159.7. And we get an answer of 142.97. And it looks like I should have 4 significant digits. So that means I can round my answer to 143.0. So that's a lot. Mass-to-mass conversions are a little bit more work than just doing mole to moles, but hopefully you see like it kind of follows the same kind of horseshoe pattern. You'll start with a mass of something, mass of some sort of given quantity. You're going to have to convert it to moles. Then you'll have to take those moles and convert it to moles of something you're looking for using the mole ratio. And then you take that those moles of the things you're looking for and turning it into the mass of the thing you're looking for. What would the mass of given turning into the mass of the, I don't know, let's call it target. There you go. Check. So this is a very common strategy. I kind of draw things in kind of angled a little bit differently, but you're always going to be converting into moles, and then with your moles, you're going to use your mole ratio to convert into moles of the thing you're looking for. What you do with it afterward can sometimes change. It might not always be mass. Sometimes it might be a concentration, might be a volume if we're dealing with a gas, but like this thing here, doing a mole ratio and converting between moles is the link. It's the common item whenever we're doing any sort of stoichiometry. All right. Thanks for watching, and I'll see you in the next video.